Next up, I'm happy to introduce François Chollet. François is an AI engineer and researcher working at Google. He is the creator of the Keras deep learning framework and the author of the best-selling AI textbook, Deep Learning with Python. François, over to you.
Hi, my name is François. I work at Google on the Keras team. And what I love to do is to build tools to support the workflows of machine learning developers. Not just developers at Google, but developers across the industry, since Keras is an open source project. And today, Keras is 7.5. TensorFlow is a bit younger. It will turn 7 in November. In that time span, TensorFlow has become the most used machine learning platform. It's been adopted by over 3 million developers globally. It's the third most installed repository on GitHub, right behind Vue and React, and it's the most downloaded machine learning package on PyPy. It has also brought machine learning to the mobile ecosystem as well. TensorFlow Lite today runs on 4 billion devices. TensorFlow does not just have high adoption, it also has high momentum. Today, TensorFlow is gaining new users faster than at any point so far. In the 2022 Stack Overflow Global Developer Survey, TensorFlow was the #1 most wanted technology, defined as a technology that you are not yet using but that you would like to learn next. This is predictive of increased adoption going forward. At Google, TensorFlow powers virtually all production machine learning from search, Gmail, Maps, Play, Ads, Photos, and many more. And beyond Google, at other Alphabet companies, Keras is beyond YouTube's recommendations, for instance, and Waymo's self-driving cars. Waymo is using hundreds of different Keras models. In the broader industry, TensorFlow also powers machine learning for some of the largest machine learning users in the world, like Apple, Netflix, Tencent, Twitter, and many more. I believe this position that we are in is an opportunity. The thing you have to keep in mind is that this is really just the beginning for machine learning. Today, machine learning is getting adopted across more and more companies, but machine learning has only realized a small fraction of its potential so far. The majority of problems that you could solve with machine learning are still being handled by legacy solutions today. Sometimes they are not being solved at all. Over time, machine learning will make its way into every problem where it can help. It will become as commonplace as web development today. Our job on the Keras and TensorFlow teams is to facilitate this future. It's to enable developers across the industry to take machine learning and apply it to every problem where it can help. An important way we do this is by tracking and anticipating how the world of machine learning is evolving and then facilitating these trends. In the same way that Keras and TensorFlow originally facilitated the rise of machine learning in 2015 and 2016, now we facilitate the evolution of machine learning as a field going forward. We are always asking, where is the world of machine learning headed? What are the big trends that we are seeing? And what can we do to facilitate these trends and create the most value for the industry? There are 4 trends that I'd like to talk about today. The first one is how machine learning is going to become accessible to all software developers, not just machine learning experts, and how it's going to turn from an expert-centric craft into a process-centric industry, not unlike what happened with web development since the 1990s. The second trend is about scale. We are seeing larger multi-device models trained on more data. And the third trend is about deploying machine learning into the real world. Machine learning on mobile devices, embedded devices, running locally as part of web application and so on. The last trend is about safety and privacy. That's something that's going to be increasingly coming into focus in the next few years. Machine learning is about mining past data, often user data, to make decisions about the future. As we do this, there are very significant privacy and bias issues that we have to navigate in order to make sure that we build applications that are safe and beneficial to end users. So let's talk about each of these trends. Starting with the democratization and industrialization of machine learning. Today, ML development remains very constrained by expertise. You need deep ML expertise to solve real-world ML problems, in the same way that 25 years ago you needed to be an expert in order to just make a website. And most ML development efforts are still one-off. They don't use data versioning, they don't do experiment tracking, they don't do model versioning, they are not even reproducible. So machine learning today is still very much a manual craft. This is what I call hero-style development. You have typically just one person on the team, one expert that knows machine learning, and that just does whatever it takes to reach the goal, to ship the system, and everything depends on them personally and their expertise. Of course, this development model is not scalable or reliable. So what's going to happen in the next decade is that machine learning will turn from a craft into an industry. Instead of being restricted to experts, it will become universally accessible. And the hero style of development will be replaced with a process-centric, collaborative approach, organized around standard MLOps infrastructure and best practices. This basically mirrors the evolution of web development since the 1990s. Machine learning will become a new superpower in the toolbox of every developer. It will go from a niche craft into an industry as mature as web development today. And our job is to enable that. In 2022, there are an estimated 25 million software developers in the world. And this number is due to grow to almost double that number, 45 million, by 2030. And the majority of them will not be machine learning developers, of course. Their primary identity might be mobile, web, cloud, embedded systems, and so on. But they will be using ML occasionally, in the same way that today a majority of developers do web development occasionally. And that's a massive opportunity. At the core of this opportunity, there's the need to make ML universally accessible. These new developers, for the most part, they are not ML experts. They don't have this expertise. So how do we empower them to use ML anyway? I see 3 key points. First, there's UX design. You want to design software tools that are high level and easy to use, but without compromise on power or flexibility. Second, there's component reuse, in particular model reuse. Developers will not be developing brand new ML components. They will be reusing existing solutions. And the more reuse you introduce, the more accessible machine learning becomes. And the last thing is automation, automating away expert decisions. So let's take a look. How do we design ML developer tools that can be used by everyone, yet remain sufficiently flexible and powerful to handle the most difficult real-world ML problems? A big part of the answer is progressive disclosure of complexity. That's a key design principle like Keras leverages. Keras doesn't force you to follow a single way of building and training models. Instead, it enables a range of different workflows from the very high level to the very low level, corresponding to different user profiles. So you could be using Keras like you would use scikit-learn, for instance, just calling fit and letting the framework do its thing. Or you could be using it more like NumPy, taking full control of every little detail. So for instance, model building in Keras is a spectrum, from the simple to the very flexible. The simplest model you can build is with the sequential API, which only allows a stack of layers. It's a good fit for beginners, for hello world type models. Now, if you want, for instance, multiple inputs and outputs, you want to share layers, you want more complex model topology and so on, you can use a functional API. That's a good fit for most machine learning practitioners. This is what machine learning engineers at Google tend to use. Like in the case of this model, for instance, which is a mobile-based image segmentation architecture. Then you can gradually extend and customize your models by using custom layers, losses, metrics, and so on. At the end of that spectrum, you can use model subclassing, in which case you're writing your own code, and Keras only provides very lightweight scaffolding for structuring that code. Another axis of progressive disclosure of complexity is model training. The simplest way to train a model is to call the built-in fit method, just like in scikit-learn. But the fit method only covers supervised learning. So if you're not doing supervised learning, you need to write your own training loop. But you don't have to write it from scratch. An easy way to customize what fit is doing is to override a specific method on your model class, the train step method. This gives you the ability to implement a custom training loop that will support all of the built-in features, like callbacks, multi-GPU support, CPU distribution, and so on. So this is great for something like generative models, for instance, which have been in the news lately, or unsupervised learning. And finally, if you cannot use fit, you can write your own low-level training loops entirely from scratch. This is what you're doing if your use case is something like reinforcement learning or meta-learning and so on. So very advanced research use cases. So you have a spectrum of workflows from the basic to arbitrary research use cases. One important outcome of this philosophy is avoiding silos. Silos are bad. You don't want to live in a world where there are three incompatible ways to use machine learning, three API silos. On one hand, the high-level scikit-learn type way, where you're using the built-in features that they are easy to use, but then you're constrained to these features, you don't have a lot of flexibility. On the other hand, you have the low-level way for researchers where you're writing everything from scratch, which is very flexible, but it can only be approached by experts. With Keras, there are no API silos. Instead, you have access to a spectrum of workflows, and because these workflows are based on shared APIs, components from any workflow can be used in any other workflow. They can all talk to each other. And because of that, Keras can be used by college students, but it can also be used to produce arbitrarily advanced technology, like this Path Dreamer model from Google Research. This is a model that can predict the contents of previously unseen rooms in a building from a single observation. So that's how UX design can help make machine learning widely accessible without compromising on flexibility. But that's not sufficient. Another key element of the solution is to encourage reuse and standardization. Today, most deep learning workflows are still very inefficient because they involve recreating the same kinds of models over and over again and retraining these models on similar datasets over and over again from scratch pretty much every time. Most of the work we do does not get reused. And so there's a big contrast between, on one hand, traditional software development, where reusing packages is the default, and most engineering actually consists of assembling together existing functionality. On the other hand, the deep learning world, where you have to build your own models and train them from scratch instead of just importing what you need. The most successful programming platforms like JavaScript and Python, they feature very strong network effects. They comprise a ton of different components, where each component makes the other components in the ecosystem more useful and more valuable. They have an ecosystem of reusable parts that covers pretty much everything you might want to do. And I think that's coming to the deep learning world as well. So on the Keras side, what we are doing here to enable this is that we are expanding our API into domain-specific packages, Keras CV and Keras NLP. They provide reusable building blocks that you can use to quickly create any kind of computer vision or NLP pipeline. So this includes pre-trained models like RetinaNet or BERT. If you're a Keras user and you haven't tried Keras CV and Keras NLP yet, definitely check them out. They're still in development, they're still expanding fast. If your workflow is already part of what's currently supported, then you can expect to make your code a lot shorter just by adopting building blocks from these two packages. The last thing you need in order to unlock the ability to do machine learning with less expertise is to automate everything that can be automated. Today, a large fraction of deep learning development is still about tuning the hyperparameters of your model, which is very high expertise. And in my opinion, that's not a job for humans. In the next 3 years, we are going to move beyond handcrafting architectures, beyond manually tuning your learning rate and constantly fiddling with, small configuration details. ML workflows will become increasingly high level. Today, there are still tons of decisions you have to know how to make. There's this expertise bottleneck. And for many use cases, that's going to change. An important part of this story is Keras Tuner. Keras Tuner is a feature-complete hyperparameter tuning framework. It's what you use to tune the parameters of a Keras model. And if you want to go even higher level than that, Keras Tuner is also the foundation for AutoKeras. AutoKeras is an end-to-end AutoML package where you can create and train Keras models in just one line. All the configuration decisions are made automatically for you. The second trend I want to talk about is scale. Models are getting bigger, and they're being trained on more data using faster chips and larger clusters of them. There are two axes of scale that we are looking at. There's data parallelism, where you're training a regular-sized model using more devices to make it possible to train it faster or just to train it on more data. And then there's model parallelism for models that do not fit on a single device. Nowadays, many language models and vision models are increasingly becoming multi-device models. Let's take a look at data parallelism. In Keras, the model distribution logic is independent from the model definition or from the code that you use to train the model. So you can take any model you have that trains on one GPU and you can turn it into a multi-GPU data parallel model in exactly 2 lines. Here's an example of a local single device workflow. You build the model, you define some metrics, you compile and fit the model. This could be using a custom train step, for instance. It doesn't have to be just a built-in fit loop. And let's say you're running on VM with 8 GPUs. You just need to define the distribution strategy that you like to use. Then you create the model inside a strategy.scope, and that's it. You have a data parallel model training on 8 GPUs by just adding these 2 lines. In this case, we use the mirror strategy, which replicates your model once on each device and does synchronous training across the devices. You have a range of different strategies available, including parameter saver strategy, which is what you would use to do asynchronous training across a large cluster of machines. Let's say you have 1 GPU per machine and 50 machines. This is what you would use. And this extends to TPU training as well via the TPU distribution strategy. For model parallelism, our solution is the dTensor API. dTensor is a new TensorFlow feature that's actively under development, but that you can already use today. It's fully integrated with Keras. It enables you to treat a set of accelerator devices as a single device by defining a device mesh and distributing your computation and your variables across this mesh. It's a very simple and yet powerful distribution programming model. This unlocks large-scale model parallel training and inference. The next trend that will shape ML in the next decade is deployment into the real world. Deploying ML to billions of mobile phones, to billions of microcontrollers, embedded in industrial systems, and in your browser. There are 2 key packages that we are betting on. There's TF-Lite for mobile devices and embedded devices, and there's TF.js for deep learning in the browser. The ability to run ML in the browser and on mobile devices at production level performance enables a huge range of new applications. And it's also making ML more privacy friendly, since you can start learning user-specific models that are kept on your device without remote data collection. When it comes to deploying on mobile, we've gotten great feedback from Android developers who love using TensorFlow Lite, but who don't like the burden of deploying the runtime together with their app, and then having to continually update their app to get the latest runtime. So instead, we've made the TensorFlow Lite runtime available via Google Play services with regular updates. So that way, your users will always have the latest, fastest version of TF-Lite, and your APK size will be much smaller as well. So several teams at Google, including MLKit, are already using this service. And they're serving over 400 million monthly active users, running over 20 billion daily inferences. TensorFlow Lite is used extensively in Google Photos. Maybe you already use Google Photos, and if you do, you've noticed that it includes some really cool ML features, and that's all powered by TF-Lite. That's models that are running on your device. It's not on the server. So solutions like Magic Erase, for instance, where you have a model small enough to fit on your phone that can remove unwanted objects from your pictures, just like magic. And TF-Lite also runs on microcontrollers. This means that you can start deploying ML in industrial settings, on assembly lines, for instance, at very low latency and very low power consumption. So for instance, here's an application of TF-Lite where you have an object detection model that's used to spot printing flaws during a 3D printing job, and then quit printing when it happens. And then on the browser side, we have TF.js. It's a library for machine learning in JavaScript that can run in the browser on the client side. This enables lower latency inference for a web app, better privacy, and lower saving cost. It also supports Node.js if you want to run it on the server. And TF.js isn't just a library for deploying the models that you've trained in Python Keras. It also features a large collection of pre-trained models in JavaScript that you can start using right away. So for instance, this is a face mesh model. This model is just 3 megabytes in size. and it has the ability to recognize about 500 landmarks on the human face. On the right here, you see a virtual makeup try-on demo made by Modiface, part of the L'Oréal group. The face mesh model is especially great for augmented reality applications like this one. Here's another TFJS model that's great for augmented reality. It's the body segmentation model. This model can distinguish 24 body areas across multiple bodies simultaneously, all in real time. We've seen a number of companies adopt this model, such as Include Health. They're using TFJS to build an app for remote physiotherapy diagnosis that you can use from the comfort of your home, just with a regular webcam. Last but not least, let's talk about privacy and safety. As we start deploying ML to every problem out there that it can solve, there are critical safety challenges that we need to navigate. The deployment of ML encourages data collection, which creates privacy concerns. And machine learning models, they learn from data. They turn historical data into decision-making systems that shape the future. So this raises the question of the quality of the data that you're using and the biases that may be present in your data. If you learn from biased data, and every dataset out there is biased in some way, then these biases will be enshrined into the system that you're building. And compared to an explicit algorithm or human action, biases that are present in a machine learning model, they are going to be even harder to detect and audit. So as tool makers that enable the large-scale deployment of ML, it's our responsibility to make sure that deployment happens safely. Google is a big user of ML, obviously, and for our own internal usage, we've defined 7 principles to structure how we approach responsible AI. Applying these principles means asking specific questions and running audits at every stage of model building and deployment, starting with the problem definition and moving on with data collection, ending with monitoring the deployed model in the wild. So of course you may say, this all sounds good, but it's very abstract. So to make it concrete and applicable, we've created a suite of tools and resources that we call the Responsible AI Toolkit. It maps closely to the safety questions that every ML developer should be looking at each stage of the model development process. This toolkit is fully open source and it's fully integrated with the Keras API. So if you're interested in these questions, then I encourage you to check it out at TensorFlow.org/responsibleai. And my favorite personally is the model remediation package to address bias in Keras models. Check it out. Final words. I really believe that we are at a transformative moment today, where ML is moving at an incredible speed, and problems that were thought to be too complex to solve with computers a few years ago, they are now being solved by applying machine learning. So we have this great opportunity. If machine learning becomes more accessible, the world will move faster, our economy will move faster, science will move faster. But we are not going to realize the full potential of machine learning if we wait for researchers at Google or Microsoft or Apple to solve all the problems that need solving, because the tech industry is often not even aware of the problems that need solving. You can apply machine learning to optimize fish farming in Norway, for instance, or to monitor the Amazon rainforest for illegal logging. So to realize the full potential of ML, we need to make these technologies radically accessible, to put them into the hands of anyone with an idea and some coding skill, just like web development today, so that the people who are familiar with these problems can start solving these problems on their own, in the same way that today, anyone can make a website without having to wait for the tech industry to make it for them. So that's the future that we are building, a future where machine learning is a radically accessible tool in the hands of basically everyone, every developer out there. That's how we will succeed in deploying these technologies to every problem they can solve and realize the full potential of AI. Thank you for listening, and I'm looking forward to checking out what you'll be building with Keras and TensorFlow.